Here we go. So we're going to do water potential today. And water potential is all about being able to determine which way water is going to flow. So this is it allows us to determine where water is going to flow. The symbol for water potential is the Greek letter psi. Notice that that letter looks like trident. What's the name of the Greek god that's the god of the oceans? Poseidon, Zeus's brother. And that's where that symbol came from. It's kind of like Aquaman's trident, Poseidon's trident, same thing. If you're a Little Mermaid fan, what's his name? King Triton's trident. The formula for water potential is water potential, which is what this symbol is, equals solute potential plus pressure potential. We're going to talk about what do those variables represent. There are going to be numbers that you plug in and how to determine what those numbers are, okay? In order to understand all this stuff when it comes to water potential, you need to really have a grasp of osmosis. So let's do a recap of osmosis before we go any further. Osmosis is the diffusion of what? Water. Is this an active transport process or is this a passive transport process? This is passive. Can anybody recite what the three forms of passive transport are that were on your Friday video? Go ahead, Megan. Yes.
Simple diffusion, associated diffusion.
Very good. So passive transport is all about you were going down the concentration gradient. You're going to go from a high concentration to a low concentration. And when it comes to osmosis, you're going to go from a high concentration of water to a low concentration of water. And so there's actually a few ways that you can determine which way water is going to flow. I'm going to go over the easy way, which I put in the video, and I'm going to go over a little more challenging, elaborate way to figure it out. And it's important that you just get exposed to this other way of determining which side needs more water in order for both sides to be considered stable. All right. Okay. So here's what it looked like on the video I posted for you guys last week. So you have a container here. You have a membrane. Now let's say I told you that this membrane is the same thing as a plasma membrane. So what is it mostly made out of? It's mostly made out of a phospholipid bilayer. And what is the polarity of a phospholipid bilayer? Okay, and these are the little things that you need to know for AP biology. If it is nonpolar, can water pass through it? Water cannot pass through it. So we need to have some channels. What do you call these little channels in which water can pass through? Aquaporins. Nice. Okay, so we've got our water. Here we go. So it looks like we have an equal amount of water on both sides, but guys, every little dot I'm about to draw is going to represent a solute. This could be oxygen, it could be salt, it could be sugar. It really doesn't matter. It's just a solute. A solute is something that gets dissolved into a solvent. A solvent is the majority of a solution. You know, water is called the universal solvent. It does the dissolving. A solute is the thing that gets dissolved. Okay, no tricks here. What side has more solute, the left or the right? The left. Now, you can make up some arbitrary number, but just whatever number you choose for the left, make sure that number is going to reflect the right side too. So let's just pretend that this is 15% solute, 85% solvent. That means it's like 15% salt, 85% water. On the right side, would our number be greater than or less than 15% solute? Less than. So let's just say it's like 5% solute. So what percent solvent would it be? 95% solvent. So this is passive transport. In passive transport, you go from a high concentration to a low concentration. This is osmosis. So which way is water going to diffuse? From the left side to the right side or from the right side to the left side? It's going to go from right to left because, you know, I don't claim to be a math expert, but 95 is bigger than 85. That means we need to go from high to low. So let's do that. Water is going to diffuse through the aquaporins until what is achieved? Some sort of equilibrium. So how can 15% and 85% get equal to 5% and 95%? How about 10 and 90? 15% gets dropped down to 10, and then 5% gets bumped up to 10. So we're going to change this. So here's what happens first, guys. The water levels actually change. This water level is going to elevate. This water level is going to decrease. And when that happens, you'll have an equilibrium achieved. So we have 10% solute, 90% solvent, 10% solute, 90% solvent. And there you have it. Both sides are equal. Now, one thing to keep in mind is water will always diffuse towards whichever area has a greater concentration of solute. I told you guys that about a month or so ago, I took my dog to the beach, and you know, he's a golden retriever. Sometimes he can be a big idiot. And so his name's Audie, so I'm like, Audie, don't, stop. No drinking the water, no drinking the water. Well, he decided to keep drinking the salt water. And so he's out there slurping up the salt water. He's drinking a lot of salt water. What do you think has more salt? The salt that was in the water he was drinking, or the salt that was in his own cells and his tissues in his body? The water definitely had more salt than his body does. And so what I'm going to do is I'm going to try to trace out his digestive system here. There's his esophagus. Here's his stomach. Then you have all the intestines, you know, large intestine, small intestine. And then you have the rectum and the anus. So we brought him out of the water, and he would come out of the water, and he would just start pooping. It wasn't brown. It wasn't turds. It was just straight water, completely clear water. What was happening was the water that is in his cells and in his tissues was being drawn out of his cells and of his tissues, and it was going towards the salt that he just drank. So it was all going into his digestive system. That means that the water that was in his muscle cells, his surrounding tissues, was all going towards his digestive system. And so he had all this water in his digestive system now, and he just had to get rid of it. So he just pooped several times, straight water. And he was very dehydrated after that. So we gave him several bowls of water, and he licked them all up, like 3 or 4 bowls of water. He was very thirsty. because drinking salt water dehydrates you. It does this by taking all the moisture, or most of the moisture, out of your cells and into your digestive system, and then you have to just poop it out. And you might be wondering, why didn't he pee it out? Well, it takes a little while for the water to filter from your digestive system into your urinary system, which is your kidneys. The salt was taking water from his cells far too quickly, and he just started to build up his digestive system with water, and he just had to get it out of his digestive system. When you pee, that's your urinary system. When you poop, that's your digestive system. So it just came out there. But all in all, he was fine, but he'll probably do it again because he's an idiot. Now, here's the hard way to try to figure this out, but it's worth knowing. Okay. Based on the shape, what molecule does it look like I'm drawing? I'm drawing water. It's the Mickey Mouse molecule. Okay, guys. Are both sides equal? Do I have an equal amount of water on both sides? Sure do. Now, for those of you that have not taken chemistry, here's a little crash course. I should probably use difficulty. This is sodium chloride. Sodium chloride is NaCl, table salt. Now, what I'm going to do is I'm going to place this into the water. There it is. Do you know what happens to sodium chloride when you place it in water? It dissolves, but the real word that we're looking for is that it ionizes. It's going to ionize, which means it is going to separate. Dissolve is the same meaning here. So now we have sodium and chloride, but these are ions now. So the sodium ion is positively charged, and the chloride ion is negatively charged. Okay? Everybody follow me so far? All right. Now, is water polar? Yes or no? What makes it polar? Remember? It has those partial positive and negative charges. Let's see if this jogs your memory. Remember I told you first unit is going to be tough to remember. Do you remember this? The hydrogens are partial positive. The oxygen is partial negative. So here's my $1 million question. Let's just focus on the sodium for a second. What part of the water molecule would you expect to be attracted to the positively charged sodium ion? Would it be the partial positive hydrogens or the partial negative oxygens? The partial negative oxygens would be attracted to that sodium. So here's what I'm going to do. What I just did. The water molecules are going to surround that sodium ion because they're attracted to it. But look closely. What side of the water molecules are attracted to the sodium? The oxygen side or the hydrogen side? Why is the oxygen attracted to the sodium? Say? Because the sodium has a positive charge. And what's attracted to a positive charge? A negative charge. So the oxygens of the water molecules attract to the sodium. Everybody follow me so far? It's a lot to take in. This is usually like one of the harder lessons of the year. Kind of messed up my chlorine there. Let me redraw that real quick. Okay. Now, What part of a water molecule is going to be attracted to the negatively charged chloride ion? The positive hydrogens. That is absolutely right. So here's the big question, guys. Which side of the membrane has more free water molecules now? The left side or the right side? The way we view this is those water molecules that are now bonded to the sodium and chloride ions individually, they're no longer free. They're all caught up in electrostatic attraction. So what we need is we need water molecules from the left side to diffuse over to the right side in order to make things equal. Here's another way to look at it. Which side has more solutes? The left side or the right side? The right side has more solutes. So if I go back to the example of my dog, the dog just drank a bunch of salt water. What has more salt? His cells or all the water that's in his digestive system right now? The water that he just drank that's in his digestive system. So what happens to the water that's in his cells in his body? It gets drawn to the area with all that sodium. That's how that works. And so, if I just plug in, imagine I put in a few aquaporins, how many water molecules need to diffuse to the right side in order for things to be equal again? Okay, so we'll do 3. 1, 2, 3. Because how many are now on the left side? It's going to be equal. Now, what if I did this? Check this out. I'm going to put these back here. I want to go over those terms, hypertonic and hypotonic. Which side is more hypertonic than the other side? And before you answer this, here's how you do it. You have to ask yourself, which side has more solutes? Which side has more? The right side. The word hyper means too much or high. You know, if you were watching Star Wars and they say, okay, let's go to hyperspeed. Pull it back, whoosh, you're off. Hyper means a lot, like let's go to a lot of speed. The opposite of hyper is hypo, which is not enough or low. According to my own eyes, the right side has more solute than the left side. So there's multiple ways in which we can say this. One, we could say the right side is hypertonic to the left side. What's another way you could say it? Flip it. What is the left side compared to the right? You would say the left side is hypotonic to the right. Hypo means it has less solute. But now, let's make things equal like I did a moment ago. 1, 2, 3. What do you call where both sides are equal? Isotonic, that's right. Now, diffusion doesn't stop, guys. Let's say one water molecule diffuses over here. So what do we have to do to make it equal again? Make one come over here. That happens a lot. In an isotonic environment, you might have X number of water molecules diffuse across a membrane. You have to have the same amount of molecules diffuse back the other way. So that's the tricky way in trying to determine which side is going to get the water flow. Let's go back to water potential. Okay. So let's say I have an example here of a cell. And inside the cell, the water potential is negative 40 bars. We measure water potential in bars. It's measurement of pressure. The water potential outside the cell is negative 5 bars. Which way is water going to flow? I don't know. This is what you have to interpret. So, fun fact. Water flows towards the region with a lower water potential. So what is the lower number, -5 or -40? Last I checked, -40 is less than -5. So water is going to diffuse into the cell, possibly swelling it up and blowing it up. Okay. Now let's apply this to more biology here. I'm going to draw a tree. Okay. Trees take in water through their roots, so water has to be able to go from the ground into the roots. Well, how does that happen? Roots don't have a straw. They can't just suck up all the water. We have to go with water potential. So let's say that the ground has a water potential of 0 bars, but the roots have a water potential of -2 bars. So the water is going to diffuse into the roots. In the roots, you have solutes like sugars and amylose. And then we're going to talk about the stem. Let's say the stem is -6 bars. So which way is water going to flow? Stem to roots or roots to stem? Roots to stem, that's right. Let's say up in the leaves, you have -15 bars. So water's going to go from the stem to the leaves. And then in the atmosphere, it's -1500 bars. What do you call the form of evaporation where water is lost by a plant into the environment? It begins with a T. Transpiration. So water just goes up, 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 and eventually will, if the plant can't hold it, it's going to lose water to the atmosphere through evaporative forces. There's a lot of solutes that are up in the atmosphere, different types of gases. So water always likes to go towards whichever region has more solutes. The lower the water potential, the greater the amount of solutes. And up in the atmosphere, you have oxygen, you have carbon dioxide, you have methane, you have nitrogen, all those different solutes. And when you say air, when I teach chemistry, if I have a student say, what are states of matter? And they go, solid, water, and air. Like, hold on. Water is not a state of matter. I think you mean liquid. In air, there's not just air. You know, our atmosphere is oxygen gas, carbon dioxide gas, nitrogen gas for the most part, a little bit of methane, a few other things. It's not just air. Air is a mixture. It's a solution. So this is to demonstrate how water is always going towards the lesser number. Okay. Now, talk about pressure potential here. Guys, more often than not, you're going to be given the pressure potential, but keep this in mind. If provided an open container, pressure potential equals 0. You might be given a cell or some sort of container. You'll be given that value in the word problem. Or you might have to solve for P. In chemistry, for those of you that have taken it, you don't need to write this down. This might look familiar. This is the ideal gas law. How many variables are there? 5. In any given word problem that you're given in that class, you are given 4 out of 5 of the variables. So in the water potential problems, there's 3 main variables. You'll be given 2. You have to find the 3rd. That's all. So when I say that you will either be given pressure potential or you might have to solve for pressure potential. But if you have to solve for it, that means that you'll be given the solute potential and the water potential. Now for the other one, let's get to the conclusion here. Solute potential is a little bit more to it. In solute potential, there's a problem within the problem. In order to determine psi s, you have to be able to calculate -ICRT. Now, before I go any further, these formulas are on your formula sheet on the AP exam. And any formula that's on the AP exam that you are given, I will give you too. You'll see that there are other math problems throughout this year. Not a lot, but they are there. Because you are given the water potential formula and you are given what negative ICRT stand for, I'll give that to you if you need it on your test. You don't need to worry about memorizing it, but you do have to know how to use it. If I gave Sage a brand new bicycle and he didn't know how to ride a bike, then the bicycle is pretty much useless, isn't it? If I gave you the formula for water potential, but you didn't know how to use it, giving it to you is pretty pointless. So let's go over what I, C, R, and T stand for, and then we'll do a practice problem. So the first one is I. This stands for the ionization constant. Think back to the example I did earlier today with the sodium chloride. How many units is that right there? How many units is sodium chloride? I'm not asking you how many atoms it is. I'm not asking you how many elements it is. I'm asking when you have sodium chloride, how many units is that? One. Right. One. But when you put it into water, what happens to sodium chloride? It separates. What's that term called? It ionized. That's why this is called the ionization constant. So here we have the sodium ion, and we have the chloride ion. How many units is it now? That's right. So we would say that I equals 2. For those of you that have not taken chemistry, this is a little funky, but here's how I can try to break it down for you. This is an ionic compound. An ionic compound is a metal and a nonmetal. Whenever you have an ionic compound, you throw it in water, it ionizes completely. Here's another one. Calcium chloride. You have calcium ion and 2 chloride ions. How many units is a calcium chloride molecule or compound? 1. How about 1 calcium and 2 chlorides? 3. So what is the ionization constant? It went from 1 to 3. The ionization constant is 3. What this means is that it broke apart into 3 different pieces. Yeah.
This isn't hydrolysis.
This is not hydrolysis. Hydrolysis is in biological systems. This is just, basic chemistry. It's a decomposition reaction. I heard someone say 4. So I need to clear that up. If I were to draw calcium chloride, here's calcium. It's bonded to 2 chlorides. Altogether, it's 1 unit. But when you throw it into water, it's going to break apart into the calcium ion, a chloride ion, and a chloride ion. How many units did it become? It ionized into 3 different ions. So we would say that the ionization constant is 3 in this case. Are there any questions with that? Now, here's a final example for this. C6H12O6, glucose. What type of elements are carbon, hydrogen, and oxygen? Are they all metals or are they all nonmetals? So is this an ionic compound or is this a molecule? It's a molecule. And when you put a molecule into water, do you know what happens to it? It doesn't separate. So when I throw it into water, its ionization constant is still 1. This is because it is made up of all nonmetals. It is molecular. Hear me now, 6th period. All sugars, I don't care what, glucose, sucrose, maltose, lactose, galactose, chitin, glycogen, peptidoglycan, amylose, I don't care. Whenever you are trying to ionize a sugar, it's going to be 1. The ionization constant is always 1. Because you don't hear ion when you talk about a molecule. It's 2 different things. An ion is either a charged metal and a nonmetal bonded together. Molecules don't have metals, so there's no charges. There's no ions to be had. How can you ionize if you're not an ion? Okay, any questions? All right, second variable. C, stands for concentration. In chemistry, what do we measure concentration with? What is the unit of measurement for concentration? Molarity is a good job. What is the symbol for molarity? And how do you solve for it? Moles over liters. Volume, same thing. Okay, so concentration is a number that you will be provided. It's going to be measured in molarity, which is a capital M. Still with me, Dan? R is a constant. You don't need to worry about trying to find it or make sense of it. It's just 0.0831. That's it. Just know that it's 0.0831. You'll be provided that on the formula sheet. And then lastly, we have T. Stands for temperature in Kelvin. Anybody know how to solve for Kelvin? You take your temperature in Celsius and you don't multiply it. You add 273 to it. That's all you have to do. So if I was at 10 degrees Celsius, what is that in Kelvin? 283. If I was at 0 degrees Celsius, what is that in Kelvin? 273. That's it. If I was at negative 10 degrees Celsius, what would that be? 263 Kelvin. Right. Okay, and that's it. I mean, I think it's not so easy. That's it. It's easy for me to say. Let's see if you guys can do a word problem now. Okay? Here we go. The molar concentration of a sugar solution in an open beaker has been determined to be 0.2 molar. Calculate the solute potential at 22 degrees Celsius. Which variable are you being asked to find? Water potential, solute potential, or pressure potential? You have to find solute potential. When I teach chemistry, you all know there's a lot of math in that. I can tell you that the majority of students' mistakes is that they are not pursuing the appropriate variable. All you have to do is read. In fact, I used to give a quiz where all they have to do is just read the problem and tell me what you're trying to find. That's it. You have to know what you're looking for if you're going to actually do it right. So let's do this right. Here we go. I'm going to use a highlighter here, highlight different parts. The molar concentration of a sugar solution in an open beaker has been determined to be 0.2 molar. So what variable is that? That is C, 0.2 molar. I already have R because that's a constant, 0.0831. Are you going to find a constant in a word problem? No, it's a given. We have to find I. I is the ionization constant. What type of solution do we have? What does that tell you? The ionization constant, I should probably use a different color. Hold on. The ionization constant, or we have sugar there, it's going to be 1. And then we have the temperatures in 22 degrees Celsius. What would that be in Kelvin? 295, because 22 plus 273 is going to be 295. Okay, so all you have to do is just put them in, plug them in. Don't forget the negative. A lot of people forget the negative. Get your calculator out. -1 times 0.2 times 0.0831 times 295. Your answer is going to be in bars, because technically, here's how this looks. Bars times liters, moles times Kelvin. Because you're doing molarity, liters and moles cancels out. Because you're doing temperature, Kelvin cancels out. So all that's left is bars. So raise your hand when you have an answer. Give me the whole raw answer from your calculator.
-4.9029.
Okay, now that number is a little big. We need to lower that. So you need to go back to chemistry again. We're going to do significant figures. When you're doing significant figures in multiplication, here's the rule. When multiplying and dividing, the answer has as many sig figs as the number in the problem with the fewest sig figs. So how many sig figs is the number 1? That's 1 sig fig. How many sig figs is number 0.2? 1. How about 0.0831? 3. And how about 295? How many? 3. So how many sig figs should our final answer have? 1 or 3? 1. So what is -4.9029 bars is 1 sig fig? -5. That's it. Questions?
So let's say you give us a problem, like we were doing with the examples earlier. If it's not sugar, will you give us one where it'll be like water is added and makes this compound?
I'd say you have a solution with sodium chloride. You have to know that sodium chloride ionizes into sodium and chloride ions separately, so that would have an ionization constant of 2.
Okay.
If it's not a sugar, then it would be something ionic. And if it's ionic, you just have to ask yourself, how many ions are making this up? If it's something like, if it's like sodium fluoride, how many ions make that up? 2. What if it was?
But it'll always be broken down on that.
Yep, it'll always be broken down. No, that's not it. What if it was nitric acid? How many units is that? 4. 3 hydrogens, 1 nitrogen. That would have an ionization constant of 4. Anything else? Okay.